Good morning to all. Myself, Professor Prashant Mahajan, working as an assistant professor at AISSMS Institute of Information Technology. So, in the last lecture, we have seen conductometric titration. So, we have seen four titrations. So, this is the alternate method for volumetric titration. So, in volumetric titration, we are using indicator to note the color change. But in the case of conductometric titration, we are going to note down the conductance of the solution, and after that we are going to plot the graph, and finally we will get the end point of the titration. Similarly, today we are going to see the pH metric titration. So what is pH? So from 12th you know that what is pH. So pH, it is nothing but minus log to the base 10 of H plus ion concentration. So this is pH of the solution. Similarly, pOH is minus log to the base 10 of OH minus ion concentration, and pH plus pOH is equal to pKw is equal to 14. So this term pH was introduced by Sorensen in the year 1909. So that is pH. Then there are two types of buffer. One is acidic buffer and second is basic buffer. So what is acidic buffer? How it is prepared? So acidic buffer, it is prepared by mixing weak acid with salt of weak acid and strong base. Means what? Weak acid, as we see in the last lecture, that is acetic acid, and salt of weak acid and strong base, that is acetic acid is a weak acid and NaOH is the strong base. So that is one acidic buffer. Similarly, basic buffer is there, that is weak base with the salt of weak base and strong acid. So NH4OH is the weak base and strong acid is HCl. So what is buffer solution? So buffer solution is the solution which resists change in the pH um, on addition of small amount of acid or base. How it works? So you can see from the below diagrams that action of buffer solution. So you can see, suppose we are considering basic buffer solution. So we are considering NH4OH and NH4Cl. So on dissociation, NH4OH will give you OH minus and NH4 plus. Similarly, NH4Cl will give you Cl minus and NH4 plus. So when we are going to add acid in the basic buffer solution, that H plus of the acid will combine with the OH minus of the base and it will form H2O. That means there is no effect of this H plus on this basic buffer solution. Similarly, when we are going to add OH minus in the basic buffer solution, that OH minus will combine with NH4 plus and it will give you ammonium hydroxide. So ammonium hydroxide is already present in the solution. So that means it will not going to change the pH of the buffer solution. Similarly, you can consider the case of acidic buffer. So you can see this is the acidic buffer, that is acetic acid giving H plus and acetate ions. Similarly, sodium acetate will give you sodium plus acetate minus ion. So when we are going to add OH minus in the acidic buffer solution, so that OH minus will combine with this H plus and it will give you H2O. Similarly, when we are going to add H plus in the solution, that H plus will combine with the acetate minus ion and that will produce acetic acid which is present in the solution. That means that will not change the pH of the acidic buffer and basic buffer. So change will be there, but it is up to small extent. That means up to 0.02, 0.03. Okay, so that is the action of buffer solution. So the next is pH metric titration of acids. So as we know, the first step is always the standardization of pH meter. So you can see the part 1, that is procedure part 1 is standardization of pH meter. So first one, we have to calibrate the pH meter. So for that, connect the glass and calomel electrode to the pH meter and pH meter to the electricity. So we have to connect the glass and calomel electrode. So in that, glass electrode will act as an indicator electrode and calomel electrode will be acting as a reference electrode. Clean the electrode with the distilled water. So we have to clean the electrode which is previously used in the last experiment or last batch, we have to clean that electrode with the distilled water. Then keep the temperature knob on temperature of the solution, that we are going to keep it as 25 degrees Celsius. Then keep the functional knob on pH. So pH meter is having or pH meter is the application of potentiometer. Means what? There is when you are going to see the pH meter, there are two functions. One is millivolt, that is the measurement of potential, and other is pH. So we have to keep the functional knob on pH. Then immerse the electrode in pH 7 solution. If the digital display is not showing pH 7, then adjust by using calibration knob. So we have to calibrate that pH meter. That means we have to put that or keep that glass electrode in the pH 7 solution. If it is showing PS7, then it is okay. If it is not showing PS7, then you have to calibrate, use the calibration knob and make that pH 7. Then remove the electrode from pH 7 solution, clean with distilled water and keep sorry, deep in the pH 4 solution. If the digital display is not showing pH 4, then adjust by using slope knob. Okay, so you can see, if you are using pH 7, then you have to use calibration knob, and when we are using pH 4 solution, then we have to use slope knob. But in both cases, we have to check whether the pH is showing pH 7 or pH 4. If it is not showing, then we have to just calibrate that pH meter. Then next, last step is remove the electrode and clean with distilled water. Repeat above steps to ensure the standardization. Then the second part is titration of strong acid versus strong base. So as in the case of conductometry, we have taken HCl in the beaker and NaOH in the burette. Similar is the case, but in that case, we are going to measure conductance. So we got V-shaped graph, and in this case, we are going to measure pH. So we know HCl is the acid, so the conductance will be from 0 to 7, and NaOH is the base. Then the HCl is the acid, so the pH of the solution is below 7, and if NaOH is there in the beaker, then the pH will be above 7, that is up to 14. So what we have to do? So see, wash the electrode with the water, then pipette out 25 ml of HCl solution in 100 ml beaker. Keep the magnetic stirrer on. So we have to take or pipette out 25 ml of HCl solution in the 100 ml beaker. Then fill the burette with standard 0.1 normal NaOH solution. Immerse the electrode in the solution in beaker. Note the pH at initial. So we have to take pH for 0 ml of NaOH. So as we know, HCl is the strong acid. The pH will start from 2 to 3. Add 1 ml of burette solution. Stir using magnetic stirrer and note down the reading. That is, when we are going to add 1 ml NaOH, that pH will going to be increased. So it will increase slowly up to the end point. Similarly, the pH of the each ml of the solution of burette is noted. Note down 4 to 5 readings after second sudden increase of pH is observed. Means what you have to do. So you can see the graphs directly. So this is your graph HCl versus NaOH. So we are having in beaker HCl and we are going to add NaOH from the burette. So as we know that HCl is the strong acid, so HCl is having pH from 0 to 2. So we are going to add NaOH. That means what? That HCl is going to react with NaOH. That means what? That HCl is going to be reduced from the, or it is going to be, the concentration of HCl is going to be vanish from the solution and it is going to be neutralized by that NaOH. So that is HCl, that pH is going to increase slowly. That means up to the equivalence point, the solution is having HCl. That's why the pH is below 7. Okay, at equivalence point, the solution is having equal ml of HCl is equal to the ml of NaOH. So at equivalence point, HCl is equal to NaOH. After equivalence point, that ml of excess ml of NaOH is added in the solution. That's why the conductor sharply increases up to 12. So you can see before equivalence point the solution contained HCl. After equivalence point the solution contains excess of NaOH. That's why the curve is obtained. So that is called as S-shaped curve. And as we know that HCl and NaOH is a strong acid and strong base, that's why we are getting equivalence point at exactly 7. So that is the first graph, that is pH versus ml of NaOH added. Similar way, if you do the calculation, you will get the second graph, that is delta pH upon delta V versus ml of NaOH. So you will get peak, and that peak, it is nothing but the end point of the titration. Similarly, you will get this third graph also, delta square pH upon delta V versus mean V. So that are the three graphs for pH metric titration of strong acid versus strong base. And this is the diagram of electrodes dipped in the beaker. So that's it for pH metric titration of HCl versus NaOH. So that's it from today's lecture. Thank you.